So just so we know where we are on the schedule, we are second week. Today, our hope is to go through basically solar radiation. And I guess I'll repeat this at the end of the class, but make sure if you have, and also today we will go through some examples of, specific examples of projects towards the end of the class that you can potentially work on. My hope is to assign the teams and the topics by, let's say, tomorrow. So by Thursday, you know what you're working on and you can start working on it. Because after that, you basically only have about a week and a half before your assignment. So I just want to make sure you have enough time to work. I know some of you already emailed me your preferences and team members as well. So just if you haven't and if you would like to, you can email me. You don't have to, so if you don't, then I will just assign as I deem best. Okay, so it's time. Let me go to the notes. Okay. Any questions about the class or anything else before we go on? Okay, guess not. Great, so let's jump right in. Okay, so of course this is optics for energy, and perhaps the most important source of energy for us is the sun, and we need to understand two things in this class basically about sunlight. One is the fundamental nature of light itself and how to measure it, how to analyze it. And the second thing is we need to understand something about our specific light source, which is the sun. Right? We need to understand things in general terms, just so we can deal with other light sources, like a lamp or fire or whatever, right? Because those things can also be sources of energy. But the sun is specific, so it has certain spectra we need to deal with and things like that. So we need to kind of have some basic understanding of this. So first of all, we know sunlight is the source of all of Earth's energy. Provides both heat and food. Of course, food means that you have photosynthesis, so energy in terms of light gets converted into a chemical energy. It's actually a potential energy. Chemical energy then gets converted in our bodies into whatever kinetic energy as we need. So that's a fairly complex process. Now, fossil fuels are what we use primarily for energy today, and these are essentially stored solar energy from millions of years ago, right? So fossil fuels are essentially represent carbon-based materials that have been converted into fuel over millions of years on the Earth, like dinosaurs and plants and whatnot. So everything can be traced back to the sun. So this is an important thing to keep in mind. Of course, when we think about fossil fuel that's more near term, this is referred to as biomass, which is basically things like plant matter and wood and things like that people use for cooking and for fuel and things like that. So that's referred to as biomass. This is more recent. It converts solar energy to fuel. Now, even wind energy, for instance, is the result of heated air by the sun, because some parts are hotter, so the wind moves from the air expands and it moves from the hot part to the cold part, so that creates wind. And so wind energy can be thought of as solar generated, and of course it's also affected by Earth's rotation. So we won't talk too much about wind, but just keep in mind that if you think about it from a fundamental point of view, it can also be traced back to the sun. And we all, as we talked in the last lecture, even hydropower is generated by the sun, right? Because evaporated water, the water from the oceans, evaporate by the sun, returns to the earth as rain and fills the dams, which we then use to run hydropower. So kind of, in a sense, all of energy comes from the sun. In fact, everything one can think of except for nuclear energy, right? Man-made nuclear energy to some extent is not from the sun. Also, you can imagine maybe geothermal energy, right? Produced from the Earth's core. Heat from the Earth's core is probably not necessarily related to the sun in any case. So that's kind of the context that we want to start with. Now, so that's kind of the context of the sun, but in order to understand light itself, we need to understand the physics of it. So a basic property of light is what's referred to as the wavelength. Okay? So light from quantum mechanics can have two manifestations at the same time. So one can think about light as particles, like billiard balls, flying through space, and those are referred to as photons, or they can be thought of as waves, like waves in an ocean, right? These are electromagnetic waves. And what's interesting is that light exists as both at the same time. So this is kind of the idiosyncrasies of quantum mechanics, right? So some of you have seen this before. So we are going to dive right into it and kind of try to tease out the most important things that we need to understand. So first we'll think about light as a wave. So light is an electromagnetic wave. So there is a spectrum. And what does that mean? Now, first of all, what does an electromagnetic wave mean? So this is not a class on electromagnetics, so we won't go into the deep physics of it, but basically electromagnetic wave is nothing other than, if you think about a wave as something that changes with both time and space, so it's oscillating in time, but also moving in space, right? So your function that changes in both time and space, that's referred to as a wave. Now the question is, okay, what is changing in time and space? Okay, in an electromagnetic wave, what is changing is the electric field. And associated with a changing electric field, there is a magnetic field. This is what's referred to as Faraday's law. But we don't need to understand any of that. Just we need to know that light, when we talk about light, in terms of a wave, it is a changing electric field, which is of course coupled to a changing magnetic field. When we say there's a time-varying electric field, there is always a time-varying magnetic field. That just comes from Faraday's law. So we only need to talk about one. So there is an electric field that is changing both time and space. Okay. Now, when there is a wave, the wave can be characterized by essentially two numbers. One is the wavelength, which is an important thing we'll talk about right now. And the second number is the energy, right? How much power is in the wave. We'll talk about that later on. So today we'll focus on the wavelength. Now, wavelength refers to, so if you have a wave, how far apart are the peaks of the wave? Okay, so this represents, discriminates light among different wavelengths on a spectrum. So this is what's referred to as the electromagnetic spectrum. And here it represents waves from radio waves where the wavelength is a kilometer, can be very, very long. These are radio waves that travel across continents, right, across the entire planet, all the way to gamma rays, whose wavelengths can be 10 raised to minus 12 meters. So they're incredibly, incredibly short. And this is pictorially shown here. These wavelengths are huge and these are get crunched together. Now, of course, when we talk about the sun, the vast majority of the energy from the sun is in the visible, right? And there is a reason for this. In fact, the reason is because most animals on the earth, and including humans, have evolved to essentially see in the visible because most of the energy from the sun is in the visible. Okay. If in some other alien planet, if most of the energy was in the microwave, for instance, those beings would have evolved to see in the microwave. Right? So that's kind of the interesting caveat to this whole discussion. But in any case, we need to have a sense for the scale. So you go from very, very large kilometers to nanometers. Right? So for visible light, which is what kind of most of what we will focus on, is about 10 raised to minus 6 meters, which is 1 micrometer. Okay, so keep that number in mind. We'll also talk a little bit about infrared light, which is about 10 micrometers, 1 to 10 micrometers. This is referred to as infrared. And the various grades to this, we'll come to that later on. And this is ultraviolet and X-rays and so on. Now, so the wavelength is decreasing from left to right, but the frequency is increasing from left to right. So the frequency and wavelength are opposites of each other, and we'll see how they're exactly related shortly. Okay? Frequency refers to how many times per second is that wave oscillating. So remember I told you that it's changing in both time and space. Wavelength represents the variation or the change in space. Frequency represents the variation in time. So the field is oscillating in time. So the slower it oscillates, the longer the wavelength. So radio waves oscillate much slower than gamma rays. Gamma rays oscillate really, really, really fast. Okay? So one thing you can start thinking about intuitively is how does the energy change? So I told you energy is the second property that we'll think about later on, or the power. How does that change if you think about this kind of a situation? Will something oscillating slower, or something oscillating faster will have more energy? I think you can think about this. I mean, this is not, you don't need to discuss, but basically you can think from a common sense perspective, something that oscillates faster will have more energy. And that's exactly right, and we'll show that shortly. But you can imagine intuitively that as you go from left to right, the power in the photon, or the energy in the photon, increases because it's oscillating faster. Okay. Also keep in mind the colors here. So this is the visible part of the spectrum. We know this rainbow. As you go into the red, it's infrared. As you go further into the blue, that's ultraviolet. Okay, so this is kind of the landscape that we have to study of light. Now, what are the properties and how do we relate them? So as I said before, the light exists as a wave, right? It's an electromagnetic wave, and the wave is defined by wavelength and frequency. Wavelength and frequency are related, so we'll see that shortly. But as I said before, in quantum mechanics, light is also a particle, like a billiard ball, right? And the particle is not defined by wavelength or frequency, but it's defined by momentum and energy, right? If you have a football that's traveling in space, it has a momentum, right? Like a car. It's of course kinetic energy associated with it. So that's how you define a particle. But what's interesting is that a light is a wave and a particle. So all of these are interrelated. They're interrelated by this very simple equation, where the energy of a photon is equal to a constant value, h, multiplied by its frequency, nu. Okay, this is the Greek nu. H, of course, as many of you have seen, is what's referred to as Planck's constant. We'll talk about that later. But it's just a constant. It's fixed. It's a fixed number. So you can see the energy is directly proportional to frequency, which is consistent with our intuition here. I told you this is frequency increasing from left to right. It's oscillating faster, right, as you go from left to right. And the energy is also increasing. In fact, they're linearly proportional. Okay, so for instance, the gamma ray photon here, which has 10 raised to 20 hertz, is about 10 raised to 16 times more energetic than a radio wave photon. So it's a linear relationship between frequency and energy, as you can see in this equation. Okay, so that's the intuition I want you to gain from this. Now, how do we relate this to, oh, hold on, let me quit that so that doesn't disturb us, my students. So now then the next question is, how do you relate the frequency to wavelength? Yes, go ahead. Okay, I'll wait till it comes back on. I had to just quit the Slack. So, is it back on? Let's see. It's on? Okay. Might just be a little lag. Let me know if it's okay. Okay, just give it a second. It'll come back. Let me know when it's back. Okay. No, I'm gonna turn off my video for a second. Oh. Yeah, I know it's just a little lag because of network, but it should be okay now. Let me know. Okay, just give it a second. Yeah, just give it a second, it should turn on. Is this still not okay? Let me see, sorry. Okay, now I went back. Okay, is it good? You can see my slide? Okay, perfect. So sorry about that. So what I was saying was that now, how do you relate the frequency to wavelength? Because wavelength is what you know typically what we think about and what we measure. For instance, we'll come to this when we talk about measuring sunlight. The wavelength is related to energy by h, which is the same constant, c, which is the speed of light, divided by lambda. So you can clearly see that the frequency here, nu, is related to c over lambda, or is equal to c over lambda. So nu and lambda are inversely proportional. So again, coming back to this equation here, energy of a photon is directly proportional to its frequency and inversely proportional to the wavelength, which is consistent with our intuition that the energy increases from left to right as the wavelength decreases and frequency increases. Okay, so these are opposite trends. So keep that in mind. Again, this will become important, so again, let me repeat this. The frequency of a photon is related to the speed of the photon divided by the wavelength. Okay, and this relationship will become important later on, so just keep that in mind. Now, why do we need to understand this well? The reason we need to understand this well is because the spectral content of light, in other words, how much energy is present in light as a function of its wavelength or frequency, turns out to be very, very critical into how we absorb that light efficiently. Okay? In other words, if you imagine if you had a lot of energy in the infrared, then you need to make sure that you have something which can absorb the infrared very efficiently. On the other hand, if you had a lot of energy in the ultraviolet, you need to engineer the material in order to absorb in the ultraviolet. So you can see now why you need to understand what the spectral composition of light sources. In our case, the sun. Okay? Of course, we also need to understand what the radiant, so that's what refers to the spectral content. In other words, how much relative power exists between the different colors of light. Or it could be the radiant power density, which refers to how much power per unit area or per unit solid angle exists in the sunlight. And this also turns out to be important when we design solar concentrators, for instance. We'll see this again. The angle at which the sunlight strikes an absorber like a photovoltaic cell is also important. We'll see this again later on. And of course, in most cases, you want to see how systems perform across a pretty long time, like a year, annual production of energy. So you want to see how the radiant energy from the sun varies throughout the year with the seasons and things like that as well. So all of these different characteristics become very, very important when we think about energy. And this is the basic equation we'll have to use in each of these situations. So let's try to do some examples to get some feeling for it, because that's really my goal here. Okay. So first of all, let me tell you what Planck's constant is. That is h. Planck's constant is 6.626 times 10 raised to minus 34 joules seconds. So you can see the units here are interesting. There's joules times seconds. If I multiply by the frequency, which is cycles per second, remember that's frequency, so the second goes in the denominator. And if I multiply joule seconds by frequency, I should get joules, which is energy. Okay, so it's consistent from a dimensionality point of view. Okay, so we can, because these numbers are really small, right, 10 raised to minus 34 joules seconds, so we want to come up with some more friendlier units, and the friendlier unit we use in semiconductor physics is what's referred to as electron volts. We express energy in electron volts, or EV. 1 electron volt is the energy required to raise an electron, 1 electron, through 1 volt potential. Okay, so in other words, if you have a potential, positive and negative potential and you accelerate an electron from one to the other end, how much energy does that electron gain? Yeah, this is potential energy, but of course when you accelerate it becomes kinetic energy, but it's just a unit. So 1 eV is simply 1.602 times 10 to the minus 19 joules. Okay, so this allows us to essentially express all energies in electron volts, which is a friendlier unit. Okay, now I want you to do some example problems, and this, take the 2 questions here, take about a minute, and you can discuss with your neighbors, and Dr. Tim can walk around. So first question is, what is the energy of a green photon? The wavelength of the green photon is about 500 nanometers. So the expression is right here. You can use a calculator or just get a simple rule of thumb. Okay, let me see. Feel free to talk to your neighbors. In fact, I insist. That's the whole point here. So I'll put the problem back on, sorry. Okay, 30 seconds. Of course, to solve this problem, you need to know what c is. So speed of light is 3 times 10 to the power of 8 meters per second. So Apratim, do you mind, if you have a marker, you can write on the board. Okay. Thank you. I should remind you to bring some on Thursday. So, of course, to solve this problem, it's simple. You plug in the numbers, right? So h is 6.6 times 10 to the minus 34 multiplied by c, so 3 times 10 to the 8, divided by lambda, which is 500 times 10 to the minus 9 nanometers, of course, 10 raised to minus 9. So in this class, we will go with approximate numbers, so you can ignore all the things in the front and just do the powers. So minus 34 times 8 is my 10 raised to minus 26, divided by 10 raised to minus 9 is, let's see, 26 is 10 raised to minus 17. But then you have these two zeros, so 10 raised to minus 19. So 6 times 3, 18 by 5. So roughly about 3 electron volts, right? 2 to 3 electron volts. Is that correct? I just did it in my head, but it's probably wrong. Okay, yeah, in that order. So between 2 and 3 electron volts. Okay, so that's the energy of a green photon. So again, what I don't really particularly care about the exact numbers, but I just want you to get a feeling for what those numbers mean, right? If you see a green photon, this energy is about between 2 and 3 electron volts. Now, of course, this will become important when we talk about solar cells later on. So keep that in mind, but we need to know what that is. Now, answer the second question now. What is the energy of an infrared photon? Okay, you should only really need 10 seconds to answer this. You shouldn't have to plug in any numbers. So I'll give you 10 seconds. Okay, so why did I say it's easy to answer this? Because the wavelength of the infrared photon is 2 times that of the green photon. So one would expect the energy of an infrared photon to be half that of the green photon, right? Because they're inversely related. So if the energy of a green photon is about 2.5 electron volts, the energy of an infrared photon would be half of that, approximately. Okay? So this is simple, but I want you, well, the important thing is to get some intuition. So understand that, first of all, what do we conclude from this exercise? First, we conclude that the energy of a photon is very, very, very small, right? We're talking about tiny numbers here, which is not surprising, right? That's what you expect, because a photon has no mass. The second thing we can conclude is that green photon has more energy than infrared photon by a factor of 2. Okay, these two things become very, very important in the future. So let's make sure we all kind of, that those two concepts kind of sink in. Okay, so moving on, the next thing, so this is the energy of a single photon. Of course, no one ever deals with a single photon unless you are working in quantum optics, okay, which we're not. So we will deal with lots and lots of photons. In other words, so we need to look at what's called photon flux. In other words, there's a whole river of photons coming at you, right, from the light source in the room, from the sun, whatever. So we need to understand how many photons are flying through space per time, and also per area, because the density is also important. Okay? So photon flux is defined as the number of photons per second, so that's the rate, per unit area. So if you think about this like a river, it is the rate of flow of the river per unit area. Okay? And again, this becomes very, very critical. Hopefully you will see a couple of examples in the next slide. So this determines, for instance, if you have a solar cell, let's imagine it's a perfect solar cell, that every photon that comes into the solar cell creates an electron, okay, which contributes to current. Okay, so if you have a certain photon flux, that also determines the number of electrons generated in the solar cell, right? So that photon flux determines the current of the solar cell. Okay, so that's how you connect it to what we really need. So flux is defined as number of photons divided by time times area, and it's in units of numbers per second per meter squared, as shown here. Okay. Okay, now let's look at some examples again to get a feeling for it. Well, actually, you have to define one other thing. But photon flux doesn't give any information on photon energy, right? It just gives you the number of particles flowing through. It doesn't tell you how much energy there exists in each particle. So we need, in order to compute power density, in other words, how much power per unit area is there in a stream of photons, you need to calculate that by multiplying the photon flux by the energy of each photon. Now here we are making the implicit assumption that the photon wavelength is the same for all these photons, which may not be true, which is almost never true. So just to define this mathematically, H, which is power density, is in watts per meter squared. We talked about it in the last class. It's the photon flux, phi, which is the number of photons per unit time per unit area, multiplied by the energy of a single photon, hc over lambda. Okay? It's very important to keep in mind that this whole equation is wavelength dependent. So there is a wavelength here for obvious reasons. Now phi can also be wavelength dependent. In other words, when you look at the photon flux from the sun, different wavelengths have different photon fluxes. Okay, so this H here is wavelength dependent in almost all cases. The only case where it's not wavelength dependent is in the case of a laser beam. If you have a laser beam with a very specific wavelength, this is only when you only have to consider one wavelength. So let's take a look at that very simple example. Okay. So I have a couple of questions here. Again, just as before, I want you to discuss with your neighbors, kind of think about this let's start with the first question and have a discussion. We'll spend about 30 seconds to a minute on this, okay? And again, my goal here is for you to gain intuition. So think from a very conceptual point of view. Don't try to apply mathematics so much. I mean, if you need to use the equations from before, it's fine. But try again, think intuitively. Okay. So let's look at the question. If you have a red beam, okay, so it's a red laser, okay, laser pointer. Let's assume I measure the same power density as a blue laser pointer. So I have two laser pointers, a red laser pointer and a blue laser pointer, but they both measure on a power meter. I measure the exact same power density. The question is, which beam has a higher photon flux? Okay, I want you to discuss. This is really to gain intuition. So just go through go through kind of your understanding of what those terms mean, power density, flux, and so on. So far, what you understand. By the way, the notes are all online, so you can more than welcome to take a look at them, look at the equations, go back. So does anyone have any suggestions on how to approach this? You can shout. Yes, correct. Yes, exactly right. Yes. So of course, so let's try to understand what these terms mean, because these are the new things for us, right? Power density. What does that mean? What does photon flux mean? Okay. So power density refers to watts per meter squared, right? Okay. So we know they have the same watts per meter squared. That means you imagine that two rivers both have the same energy, okay, but they're two different kinds of rivers. One is red and one is blue. So now we need to know what is the power of each of the red photon or the blue photon, right? So we know this equation. So this is the number we are trying to figure out. This is the energy of each photon. So we know that the red photon has a longer wavelength than a blue photon, right? So the wavelength is, and if you don't know it, you can simply go back and look at our wavelength. So you can see blue is on the right here, red is on the left here. That means the wavelength of red is longer than that of blue. Frequency of the red is less than that of the blue. The energy of the red is less than that of the blue. Okay, so going back to our question, the energy of our red photon is less than that of the blue photon. So, but if the two beams have the same power density, that means you need to have more red photons than blue photons, right? You have to make up for the lower energy by having more of these. Okay, so that means the red photon has a higher photon flux. I want to make sure that each of you are able to follow the logic and that intuition. Very simple ideas here. We want to start with simple things. Okay. So is that clear? Think about this for a few seconds. If it's not clear, just shout or put up your hand. If you can shout, it's better, and I can hear you. Again, if you go back and if you're confused by some of the stuff, just review it. It's simple, or ask your friends, or ask me and ask the TA. Okay? Okay, so let's move on to the next question. Was there a question? I couldn't really get. No questions up with them? Okay, good. Yeah, go ahead. Oh, Meme, it's you. Okay. Thanks, Meme. Yeah. So the next question is, if both beams are incident on a solar cell, which will produce higher current? So Again, I want you to take about 30 seconds or so to discuss this with your neighbor. So this is the red beam or the blue beam. You're pointing it at a solar cell, which will produce more current. And we are going to make a very simplistic assumption that every photon produces current, produces a electron hole pair, which is equivalent to current. We'll treat these more rigorously later on, but let's just imagine that it's perfect, right? Every red photon creates current, every blue photon creates current. So before you answer the last question, which is a trick question, let's answer this first, which will produce more current. I think it's obvious to many of you, so maybe you could just shout it out. Now you gotta shout louder than that. Come on, someone can answer this. Okay, so there is some disagreement. So let's think about this. Okay, so remember, the photon flux represents how many photons are there, how many. So the number of particles going into the solar cell per unit time, per unit area. Now I told you to address this question, we are going to make the assumption that every particle will give rise to one electron hole pair, which is equivalent to one current, let's call it. Okay, that's not the right terminology, but it's not important for the purpose. So each particle contributes to current. So if there are more particles, it'll contribute to more current, right? So let's go back to our first question. How many more particles are there? Which beam has more particles per unit area, per unit time? Red, right? Because we said that the energy of a red photon is less than that of blue. Power density is the same, so red has to make up for it by having more particles, right? So just by that definition, it has more particles per unit time, per unit area, it will produce more current. So if you actually take two laser beams and point them at the perfect solar cell and start measuring the current, you will see higher current in the red, but just because there are more particles going in. Okay, I know it's a little confusing, but you have to kind of think through it intuitively, okay? So maybe the way I'm asking might be confusing, but if you think about it, it's simple and you will get it. Now let's go to the last question, which is a tricky question. Which will produce more electric power? In the interest of time, let's spend only like 30 seconds. Yeah, you feel free to shout out, but I would say more important, just discuss with your neighbors and justify your answer. Because our goal here is to gain an understanding, not, you know. When I ask more electric power, I mean from the solar cell, obviously, right? So imagine there's a solar cell and you're shining a laser beam at it and you're measuring the power produced by the solar cell. Of course, I can replace the solar cell with any other heat engine for that matter and you'll get the same kind of results. But solar cell is nice because it's easy to measure. So you could actually do this experiment if you want. Anyone want to guess what the answer is? Did someone say the same? Okay, good. That's correct. Yes, it's the same. Why? Because it's the same power density, right? Power, electric power out of the solar cell. Now, I'm going to make a very simplistic assumption that the efficiency of a red photon is the same as that of the blue photon, which is, of course, not true in a real solar cell. But here we're going to assume that's the case. If that's the case, then they will both produce the same electric power. Okay, now we've gone through many concepts here, which you will appreciate hopefully in the subsequent weeks, but let's just recap. What does this mean? You have taken a solar cell and you're shining a red beam at it and you're shining a blue beam at it and you're measuring. You will measure higher current with the red beam compared to the blue beam, but both will produce the same power. What does that mean? That means the voltage, yes, exactly. The voltage produced by the blue beam is higher than the red beam. That's voltage multiplied by current is power. Okay, so these things are very, very important. So the color of the light going into a solar cell dictates the voltage. The flux going into the solar cell dictates current. Okay, very, very important insight. That's why I wanted to spend this much time on this. Okay, now we have to move on. Well, we'll revisit this later on when we look at more interesting practical applications. But just keep this idea in the back of your mind. Okay, so moving on to a few other properties. We have things like spectral irradiance. So this terminology is new to us, so we need to kind of understand what these things mean, right? Spectral irradiance essentially refers to power density as a function of wavelength. This is the most common way to characterize a light source. So when you look up light sources, you will see something like this. So this vertical axis is spectral irradiance, is units of microwatts or watts per meter squared, so it's per unit area, per micrometer. This per micrometer is the wavelength. The horizontal axis is wavelength, and it's in nanometers. Okay. So this pink curve here is the solar irradiance. This is in logarithmic units. So you see this is 0.01, 0.11, 10, so it's logarithmic units. That's why it looks a little strange. Okay, so this is the pink curve. This is what you see in the sun, from the sun. This is the mercury lamp, okay, which sometimes we use to mimic the sun. This is the xenon lamp. This is the halogen lamp. Now, what does this number mean? What does this curve mean? This means that, okay, if you pick at 400 nanometers, that is blue, I am getting from the sun roughly 10, maybe 20 microwatts per meter squared, exactly at 400 nanometers. Okay. Now, if I look at another color, let's say in the red, 600 nanometers, I'm getting about 20, a little more, right? So this is the variation. Now, if you integrate this whole curve, the area under this curve gives the total power density. I will come to that soon, but just be familiar with this curve. Of course, this also represents, this can also be represented as F, the spectral radiance, which is the photon flux divided by lambda, H per unit wavelength. So if you plug in the expression for H, which is phi, which is the photon, this is power flux, this is the photon flux. This is irradiance in other words. This is photon flux multiplied by 8c over lambda squared. Okay, this is just plugging in the equation from before. So you can see how the spectral irradiance varies with lambda. H and C are constants, of course. Phi can change with the source. So this is a function of wavelength as well. Okay, not so important at the moment anyway. So the next term we need to understand is radiant power density. Now this is the total power density emitted from a light source, and this can be calculated by integrating the spectral irradiance over all the wavelengths of interest. So basically we take this curve and simply integrate it across the spectrum, which is the area under this curve, or any of these curves. So we take H and we integrate it 0 to infinity, f of lambda d lambda. Okay, so let's think a little bit about dimensionality. What are the units of H? I want you to kind of think internally a little bit, and you can feel free to discuss, but the way you would think about it is H is radiant power density, should be, so from this equation, F is this thing right here, spectral irradiance. So it's microwatts or watts per meter squared per micrometer. So you're going to multiply it by lambda, which is in micrometers or nanometers or something like that. So you take this thing here, which is watts per meter squared per micrometer multiplied by micrometer. So those micrometers cancel out. What do you end up with? just watts per meter squared. Okay, so the dimensions of radiant power density is, as you expect, watts per meter squared. That's power density. Okay, so everything is consistent. So it's important to think about units because that allows us to understand what these quantities mean. That's why I'm trying to emphasize that. Of course, in most of these cases, you have to do the integration numerically because you don't have a simple mathematical model for these spectral irradiances, except for some theoretical black bodies. We'll come to that soon. So, there are many ways to do numerical integration. You're all familiar with this. I won't go through it, but, basically you can take a discretized curve like this and measure the area of this rectangle represented by this delta lambda, and then sum up all such rectangles, which is what's expressed here. Not so important for you to know this, but if you ever have to do numerical integration, MATLAB offers you plenty of tools to do this. So this is not a numerical techniques class, so I'm going to skip that. Okay, the next concept we need to understand quite well is the blackbody radiation. Now, black bodies are, as I said in the first week, everything is a black body, right? Everything that absorbs light will emit light, and that's referred to as a black body. Now, black body is basically like an idealization of actual objects. Okay, so although I said everything is a black body, really speaking, nothing is a black body. Black body is an approximation of reality. Okay, and the reason it will become very clear because it allows us to do mathematics a lot simpler, just like many approximations in physics. Okay, and the reason we need to understand this is because this allows us to analyze different light sources without having to go through all the numerical stuff. It allows us to gain intuition into light sources. So light sources such as the sun, incandescent lamps, etc. are modeled as blackbody emitters. An ideal blackbody absorbs all radiation incident on its surface and emits based upon its temperature. Okay? So a blackbody is presented by what's called radiation curve, and the radiation curve varies with temperature. So this is, for instance, this intensity, okay, which is watts per meter squared per nanometer, so spectral irradiance, same as intensity in this case. This is wavelength. So at 6,000 Kelvin, which is roughly the temperature of the surface of the sun, this is the black curve. And you can clearly see the peak intensity happens around green-yellow, which, by the way, is where our eyes have the highest sensitivity because humans have evolved to actually see this peak very, very, very well. Some other animals which live underwater, for instance, would be seeing other colors because they don't live on the surface of the earth. Okay, or some animals that hunt during night have different colors, of course. So at lower temperatures, you can see this is 5,000 Kelvin, 4,000 Kelvin, 3,000 Kelvin. You can see that the curve actually falls down, right? The amount of energy, which is the integral under this curve, or the area under each curve, goes down. So as the temperature goes down, of course, the energy emitted by the black body goes down, which is intuitive, I suppose. Hot things will emit more energy than cold things. But also you'll see that the peak wavelength shifts to the red. So things will start looking more redder. Okay? These are very important observations which we'll try to quantify next. So the spectral irradiance, which is this intensity, is governed by what's called Planck's radiation law. Now this is something you don't need to know, but many of you have probably seen this in undergraduate physics. This is the starting point of all quantum mechanics. This basically represents how much energy per unit area, per unit time is emitted by a black body as a function of the wavelength and its temperature. So you have a bunch of things here, 2 pi h c squared, h and c are constants, divided by lambda raised to 5, so it's highly sensitive to wavelength, which you can see here, right? It's very sensitive wavelength, multiplied by some complicated term here, 1 over exponent, so on this stuff. The important thing here to keep in mind is this T, that is temperature, and this lambda, that's wavelength. Everything else is a constant. H is Planck's constant, C is speed of light, K is the Boltzmann constant. We'll see that later on. Okay, no need to memorize the equation. No need to know it either. I just want you to be aware of it. Okay, this equation is how you plot this curve, these curves. You can plug in different temperatures, you will get these curves. Okay, but not important for us other than just intuition about these curves. Okay, now let's look at the total power density is then given by the integral, right? So we know this, we saw this just now. We integrate over from 0 to infinity the area under this curve. If you do this integral, in fact, all of you can do this integral by hand. It's not that difficult, right? It just looks a little complicated, but once you do this integral, just differential calculus, you will get a very simple expression. H is equal to sigma, which is a constant, multiplied by temperature raised to 4. Very simple expression and gives a very important result, referred to as the Stefan-Boltzmann law. Okay, sigma is a constant, referred to as the Stefan-Boltzmann constant. It's 5.67 10 raised to minus 8, and the units are interesting: joules per second per meter squared per Kelvin raised to 4. Of course, you can multiply the Kelvin raised to 4 here, so it goes away, and then you will get joules per second per meter squared. Joules per second is, of course, watts. Watts per meter squared is power density. Okay, so that's the total power density. So everything is perfectly consistent. Okay, now you can see that the power density emitted by a black body is proportional to the 4th power of its temperature. That's a pretty significant dependent, right? The hotter things will emit a lot more power, will have a lot more power density than colder things by a huge amount because of this T raised to 4. So just keep that in mind. Okay. Another important parameter is the wavelength plus spectral irradiance is maximum. In other words, in these curves, how does this peak value change? You can see that it goes to the longer wavelengths into the red at lower temperatures. So let's see if we can make sense of that. So to compute that is relatively straightforward. You take the Planck's radiation law, and you take the derivative with respect to wavelength, because that's that curve. You put it equal to 0. That's from calculus. We know that's how we find the peak values. And if you solve this equation, again, it's something all of you can do. This is just standard differential calculus. You will get a very simple expression here. You will find that the lambda at the peak is given by 2900, some constant, divided by T, the temperature in kelvins. This is referred to as Wien's law. What this tells us is that as temperature increases, the peak or the color of the black body, the wavelength, the peak of the black body, as temperature increases, this decreases, right? They're inversely related. Now this is a very, very important result with many, many, many applications, but let's look at a very simple application, okay? So the conclusion for this law is that the temperature of the black body affects both the spectral distribution as well as the total power density emitted. So the temperature of the black body is very, very important. We'll come back to this again and again. Now let's just look at a very simple example. So this is Orion's constellation, a picture of it. Let's look at two different stars here. One is Betelgeuse and one is Rigel. Okay? Let's ask a very simple question. As an astronomer, which star is hotter? And I'll let you discuss based on what we have learned so far. Maybe 30 seconds. Feel free to talk. And hopefully you can relate this to what we've been talking about in the last few slides. Okay, I don't hear anything. Anyone has any answers? You can shout the answer. It's okay if you're wrong. That's how we learn. Yeah. Is that clear to everybody? Because it looks bluer, right? It looks bluer, so the wavelength is shorter, right? This is redder, the wavelength is longer. So the shorter wavelength means the temperature is higher. Right? They're inversely related. So the blue, so for instance, if you make a fire, blue fire or very white fire is much hotter than a red fire. Okay? And not always true, but it depends a little bit on what's called emissivity for real materials. But most stars have very, very high emissivity, so this is true in this particular case. Okay? Okay, so let's move on. Let's move on to the sun and just have some very basic understanding of what's going on in the sun. It's essentially a big hot sphere. As many of you know, there was a probe that was shot, which was a solar probe, which was launched last week, I believe. It will reach the sun in a few months, a few years actually. I forget the exact number, maybe one of you knows, but we will actually know a lot more information about the sun when this probe actually reaches the sun. It's going to touch the corona of the sun, if I remember right. So it won't touch the surface, which is too hot, but it'll get as close as any man-made object has ever been. In any case, our current understanding of the sun is that it's a hot sphere composed primarily of plasma. The internal temperatures can reach over 20 million Kelvin, so it's really hot. And it's got very, very high pressure because of the composition of the other internal structures. So this high temperature and high pressure leads to nuclear fusion within its core. So what happens primarily, there are a few other reactions that happen, but primarily what happens is hydrogen becomes helium. So in the very, very inner core of the sun, there's lots of hydrogen, becomes fused together to become helium. Remember, helium has an extra neutron, right? So you gotta fuse two hydrogen atoms together to get helium. And that reaction produces massive amounts of energy. It's a nuclear fusion reaction, right? And that happens at very high temperatures. So this massive amount of energy essentially comes off as radiation, gamma rays and other X-rays, and visible, all kinds of photons. This from the inner core gets emitted, blasted out from the center, but quite a lot of it gets absorbed by the hydrogen ions closer to the surface. So the temperature as you go out reduces. Right? So the sun's surface, which is also referred to the photosphere, has a temperature of about 6,000 Kelvin. So if you look at the picture, you have the core, then there's a radiative zone where there's heat and light and photons traveling from inside to out. There's a convection zone where the plasma is kind of moving the heat out from the center. And people think about this as subsurface flow, so that's part of the convection zone. Then there's a photosphere, which is thought of as the surface of the sun. And that temperature, that surface, is about 6,000 Kelvin, approximately. And then there's something like an atmosphere, which is referred to as a chromosphere. Obviously, it's not a normal atmosphere, because nothing is solid here. Everything is a fluid, right? It's like a plasma. And then there are these things called a corona, which is basically huge blasts of gas and very, very hot ions. So, of course, one question we can very easily answer is what's the peak wavelength of radiation? We just look at 6,000 Kelvin, go back to our Blackbody plot, which is here. And we can say, okay, peak of wavelength, the sun looks yellow. Indeed, it does look yellow. Right? It is predicted by this simple plot. That's why Planck is the father of modern quantum mechanics, among other things. So solar spectral radiance resembles blackbody about 6,000 Kelvin. The total power emitted by the sun is the power density multiplied by the surface area of the sun. So of course sun is very big, so if you multiply everything together, you get something like 9.5 times 10 to the 25 watts. That's a huge amount of power, which is why we're talking about it. We want to try to harness that power, right? Okay. So in order to harness the power, of course, we need to understand the spectrum. So let's look at it in a little more detail here. This is the solar radiation spectrum. Again, the units are important. So vertical axis is spectral irradiance in watts per meter squared per nanometer. So the units are a little bit different than what you saw before. You saw microwatts. Here it's watts. And instead of per micrometer, this is per nanometer. Okay. So the numbers here are a little bit different. It goes from 0 to 2.5. In any case, The shapes are similar. Also, it's not logarithmic. This is what you will see in most cases. So the yellow plot is the spectrum of the sun at the top of the atmosphere of the Earth. In other words, if you were out in space, this is the spectrum you'll see, the one shown in yellow. And it relatively closely follows the gray plot here, which is the blackbody spectrum at 6,000 Kelvin. Okay. Or 5250, sorry, 5,250 degrees Celsius. Not Kelvin, so it's 5250 Celsius. The plot shown in red is the spectrum at sea level. And you can see a pretty big difference between them. And this difference, first of all, this big drop here, big dips here that you can see, are all due to absorption within the atmosphere. This is an oxygen absorption, this is water absorption, H2O, CO2, all these are absorption bands, and we'll talk more about that. Now, so this tells you already that if you're trying to build a system to absorb sunlight for space, I need to consider this spectrum. If I need to build a system to absorb sunlight on Earth, I need to consider this spectrum, and they're different. Right? And as we saw before, the difference in spectrum can make a reasonably important difference into the system, how systems perform. So that's why it's important to understand these things. Just for context, the wavelengths here go from ultraviolet, about 250, all the way to infrared, 2500 nanometers. Okay. Now, of course, solar radiation in space is quite different than solar radiation on Earth, and this is an important thing to understand. For instance, if you are building solar cells for the Mars rover, you would do it very differently than you would for solar cells for your rooftop, right? Because the spectrum that the Mars rover will see on the surface of Mars is very different than what it will see on Earth. So we have to account for these things. So it's easy to understand it. Solar radiance on an object some distance d from the sun is found by dividing the total power emitted from the sun by the surface area over which the light falls. So we can simply think about the sun as like emitting energy or light in a isotropic manner, or in a sphere around it. So the farther you are, surface area of that sphere is larger. So all you have to do is take the total power emitted by the sun divided by the area of the sphere where you are standing. Okay, that gives you the power density. So if it's Earth, you'll take the radius of the Earth, radius of the revolution of the Earth, approximately. If it's Mars, you do the same thing for Mars. If it's Pluto, it's way out here. Okay? So that's what's done here. So this is H naught, power density, is the total flux, right? Power density per meter squared. So this is power. This is power density. This is the total power. So it's watts divided by. This is watts per meter squared. This is from Stefan Boltzmann law, sigma T raised to 4, multiplied by the area of the sun, 4 pi r squared, surface area of the sun. That gives the total watts emitted by the sun. And you divide that by the surface area of the sphere over which this energy is distributed. So if you are the Earth, you use d as the orbital distance of the Earth from the sun. Okay, so you get a very simple expression here. It's sigma T raised to 4 times r squared, the radius of the sun, divided by d squared. D is the distance between the sun and the planet we're considering. So these are some examples. If it's Venus, the distance is about 108 billion meters. So you get a radius of 2,611 watts per meter squared. If it's Earth, it's about 150 billion meters, so it's 1366 watts per meter squared. If it's Pluto, it's about 1,000 times, 5,000, 6,000 times more. The power density, of course, goes down by several thousand as well. So you get a picture, right? Of course, the exact power density changes because these radii are not perfect circles, right? They go as an ellipse, as we know, right? We have, in January, we are closer to the sun than in July. July, we are a little bit further from the sun. So we know these things because it's not a perfect circle. So some people, in some situations, we have to account for this. In our class, we won't, but something you should be aware of. In order to account for it, you have some complicated expression which shows here it's h is equal to h constant, which is this what's referred to as the solar constant, multiplied by 1 plus 0.033 cosine 360 times n minus 2 over 365, where n is the day of the year. Okay. Not terribly important for us, just so you're aware of it. Okay, now of course the spectrum of sunlight varies quite a bit where you measure it on Earth, so different places have different spectra, but in order to create a standard spectrum to enable solar industry and so on, the ASTM and other organizations have come up with all these standards, so this is something you should be aware of. There's something called AM 1.5 global, which is this blue curve here, which tells, we'll talk about what AM 1.5 is shortly, but this basically gives a standard curve that everyone can use to measure their systems, whether it's solar cell, solar absorber, whatever. AM 1.5 direct is this green curve, which is only the direct part of the sunlight, ignoring the diffuse part of the light. AM 0 is the spectrum in space. Okay. We'll refer to this again and again later on. So just to understand the physics of what's happening, solar radiation on the Earth's surface, while the solar radiation incident on Earth's atmosphere is fairly constant, the radiation on the Earth's surface varies widely due to atmospheric effects, including absorption and scattering, local variations in the atmosphere, such as water vapor, clouds, pollution, latitude of location, so where is it located on the Earth, season of year, time of day, obviously. The parameters that affect that these things affect are spectral irradiance, power density, angle of incidence. And all these three things are very important when we consider the performance of a solar cell or any solar absorber. So the specific atmospheric effects are kind of summarized in this nice little diagram, where you can see the input, let's say, coming from outer space is 100%. About 2% is absorbed by ozone, 1% by dust layers in the upper atmosphere, 8% by some air molecules, 6% by water vapor, 1% by lower dust layer, and you end up only, whoops, let me zoom out a little bit. Oops. Zooming out. Get about the 70% of the light. Okay, and you also get losses due to scattering, so you get about, so total about 18% is absorbed. But 3% is scattered back into space at different layers, and about 7% is scattered to Earth. So this scattered to Earth is what's referred to as the diffuse part of sunlight, and the remaining part of sunlight is what's referred to as the direct part of sunlight. Okay, we'll come to that again. The direct part of sunlight is something that you can concentrate very easily. Diffuse sunlight is very hard to concentrate. And we'll talk more about this when we talk about solar concentrators in the future. Okay, so let me zoom out here. Okay. So the reduction in power due to scattering, absorption, reflection, change in spectral content. So this not only affects power, but also changes the spectrum. So different colors can scatter differently, which is the reason why our sky looks blue, right? It's not black. If you go, for instance, to the moon, the sky will be black because there's no scattering. This is due to greater absorption and scattering at certain wavelengths. Introduction of diffuse or indirect component of solar radiation can affect the spectrum as well. Local variations like in the atmosphere can also affect power and spectral content. So it can be fairly complex. The other atmospheric effects we should be aware of are absorption at certain wavelengths, where the photon energies are close to the bond energies of specific gases, like as we saw before, ozone, carbon dioxide, water vapor, oxygen, and so on. Far infrared light, which is wavelengths greater than 2 micrometers, 2 microns, is absorbed by water and carbon dioxide, so you don't get a lot of light which are far infrared, which is good because that can cause a lot of heat damage. Most of the UV, less than 300 nanometers, is absorbed by ozone, but of course not enough to prevent sunburn. That's why it's and that's also ozone depletion and so on. We've read about this before. This causes lots of problems. All these absorption events can cause deep troughs in the spectrum, as we saw before, those very narrow spectral gaps, basically. Dust and air molecules absorb across the spectrum and reduce the overall power. Roughly speaking, when the sun is overhead, all the wavelengths are uniformly absorbed and the sun looks white, whereas during the morning and evening, or yellowish, let's say, the optical paths are longer and shorter wavelengths are more effectively absorbed and scattered. This gives rise to the reddish color and lower power density. So for instance, if you look at the energy or as a function of time of day, of course, zero right before sun rises, peaks around noon and goes down at equator. At different latitudes, as shown here, it will be different. Right? The more north you go, the total energy goes down. And this is kind of indicated by the shadows in the bottom diagram. So direct versus diffuse sunlight is very important. As we'll see when we talk about concentrators, in radial scattering, shorter wavelengths are scattered much more than longer ones. This is why sky looks blue. About 7 to 10% of the light is diffused on a clear day. So an interesting thing to think about is the fraction of high energy photons higher in diffuse or in direct sunlight. So I will leave this as sort of a homework problem for you to think about because we're kind of running out of time here a little bit. Let me kind of explain this question. First of all, if you look at diffuse sunlight, are there more high energy photons or low energy photons compared to direct sunlight? Okay, and the answer is actually in this statement right there. So I will let you all think about that. Okay, so coming back to what does these standards mean? This AM 1.5 refers to it's referred to as air mass. It is AM. 1.5 is basically about 28% less power density than AM0. So of course out in space you get a lot more power density than on Earth because of absorption, scattering and so on, which we just talked about. And AM0 is used to characterize solar cells in space. You can ignore this. Let's come here. So this is actually an answer to the question I just asked you. So this is the direct beam vertical plane. This is the diffuse sky, and this is the human spectrum. So you can see the diffuse part of the light has more high energy photons as a fraction, right? It's more blue shifted. So you might be tempted to say, okay, I want to grab as much of the diffuse light as possible because it has more high energy photons, and that you would be correct depending upon the situation. Anyway, we'll see these things later on when we talk about actual systems. So air mass, which we just talked about, which defines those standards, is defined as the path length which light takes through the atmosphere normalized to the shortest path possible. That is when the sun is overhead. So this is when the sun is overhead, is the shortest path that light can take from sun to the surface of the earth. But if it's if it's not overhead, then it's longer and there is more absorption and scattering. So this is less power density. It quantifies the reduction in power as light passes through the air. And it's also defined as 1 over cosine theta, where theta is measured from the normal here. So what is the air mass at sunrise? Sunrise is way out here. Theta is 90 degrees. Cos of theta is 0. Cos of 90, 0. 1 over it's infinity. So you're going through a huge amount of air, right? So AM 1.5 is kind of a compromise between infinity and 1. Clearly, infinity doesn't make any sense, right? It's just 0 because there's no light there. If we take the curvature of the Earth into account, a more accurate formula can be derived, which is shown here. Again, not so important from our perspective. We only need to know this. We can also divide the direct component of the light perpendicular to the sun rays, and we can express that in terms of the air mass shown here. Not terribly important for us, but just be aware that this exists. So intensity increases with height above the sea level. So Utah and the desert Southwest, we have higher solar power. densities because we are higher up, right? And you can account also for that by including this h in this expression here. This is the height above the sea level. Also here. Not terribly important. We won't use these, but just something you should be aware of. So even on clear cloudless days, the diffuse component can be 10% of the cloud portion. Okay, so this kind of ends today's lecture. But so I just want to make a couple of quick points about the project. The projects are very important for this class, so I wanted to emphasize a few things. We have about 15 to 17 students in this class, so we'll probably have about 5 in-class teams with about 2 to 3 students per team, and 1 online team with 2 to 3 students per team as well. Probably 2. So just be aware, we have about 6 students. And these are the instructions for your assignment 1. I'll show you shortly. Please limit your presentation to approximately 10 minutes and question and answers to approximately 5 minutes. So anyone can ask questions, okay? The topics that I'm going to propose, if you haven't proposed one already, are the following: solar daylighting, solar water desalination, solar refrigeration or cooling, concentrated solar, PV or thermal or hybrid, solar water pressurization, and optics for recycling. I'll show you examples all of these before we start the class on Thursday. So talk briefly about that once we assign the teams. And I'll give you more. I'm going to stop here because this is not completely ready because I haven't assigned the teams yet. So we'll pick this up on Thursday, the rest of this. And I'll give you explicit instructions for your first presentation. Okay, so at this point I'm going to stop and see if there are any questions. Are there any questions? I went through the last part a little fast, so I would recommend that you go back and kind of try to digest it yourself. Are there any questions before the end? No? Okay, great. So if you do have questions, just feel free to email me, and yeah, we'll start with the project team assignments and topics on Thursday. Okay.